everybody. Glad to see you here today. This is the College of Education Research Colloquium. We're happy that you could make it today. Our format is that we have two speakers today, which is our usual format for faculty, and each speaker is going to take about a half an hour to talk about work that they're doing. We have Professor Ping Xin and Professor Scott Schaffer, and Professor Xin is going to go first this afternoon. After each of their presentations, we'll have about another half an hour where we can have questions, informal conversation if you want to hang around and chat with them. So we're pleased to have you all here, and I'll turn it over to Ping to start us off today.
Thank you for providing us, both of us, with the opportunity to present our research to the research community in the College of Education. So I want to thank you, Dr. Dimlin, for providing that opportunities. So here's my topic. Before I start with my presentation, I would like to share with you a line of my research that actually I was started this line of research when I was a graduate student in Pennsylvania at Purdue University. I was attracted to the fact, or surprised with the fact, that American students are not doing very well in mathematics, which is very surprising to me. So I started to do the curriculum comparison studies, research intervention studies, literature review in this area to try to find out what's the problem, what's the issue, what we can do to improve students' math problem solving performance. During the course of my research program, I started to actually identify the area that is more interesting to me, which is algebra readiness. Because this seems like the phenomenon that when American students get to the middle school, they start to learn algebra, and then a lot of students becomes really frustrated. It becomes a big surprise to me. And a lot of students, in fact, developed a phobia of learning algebra because they are not prepared during their elementary school of education. And the idea of advanced or more abstract thinking is not integrated into their early mathematics learning. So, actually, before I start my presentation, I want to introduce a lot of my research team members that are involved in this research program. Casey and Ben Wiles and Young Park, I believe, is also here somewhere. And you recently also joined our program, Professor Liu. So we have a big team members, and on the front page, I guess I recognized all these members in the team. Here's a list of my research publication that has been related to the conceptual model-based problem solving that I have been developing. Starting from single subject research study, and we also have several group design studies that to look at the effectiveness of this program. So I mentioned about I was attracted into this field because of this burning issue, national burning issue, in terms of students not doing well in math, but also in terms of they are not prepared for algebra learning later in the middle school. Let me talk a little bit about, well, what is conceptual model-based problem solving? So I believe that the representation that models the underlying mathematical relations in a problem, this is, I give an example of additive problem solving model, mathematical model or conceptual model, that will facilitate the student generalizable problem-solving skills. That means if we provide students with such a tool, they will be able to solve not only a few problems, but many similar problems or with similar patterns. Based on my research studies, it seems like it's very powerful, especially for those students with learning difficulties or disabilities, because they have limited working memory, they have limited organization skills. These characteristics really limit them to memorize or processing a lot of information in the brain at the same time, or remember numerous rules that teacher teach them to remember to decide, okay, when I use this operation, when I use this operation, or when I should use that strategy. So I found that by focusing on the mathematical model, which is very powerful for them to approach many different types of a problem, or to give them a tool that they can use to at least a way to approach the problem, and actually the model will help them to decide what operation to use. They don't have to remember the rules or rely on the rules, which is the common practice or very popular approach nowadays in the field of special education, because we talk about schema-based instruction, basically teach many types of problem structures, and the student have to remember first the different type of structure of the problem, and then remember the rules that help you to choose the operations. But with this model-based problem solving, they don't really have to do that.
Do you want questions as we go along?
Oh, yeah, it's okay, you can raise questions.
So this model is visual. Are all of these models visual, or?
It is visual. Will kind of serve as a permanent prompt during the training process. Later, hopefully, it will be internalized.
Yeah.
Students will be
But even internalized visually, and I'm just
a visual. That's right, visual.
Conceptual and visual to me are like two different things.
Yeah, it is. That's right. Combining the visual representation and conceptual understanding. So I want to present with you this model borrowed from math education. These two scholars come up with this model. I thought it's very relevant to the line of research that I have been developing. Left side, if you look at the left side, this is the real world. So when students are presented with a word problem, it is a real world situation. So it's a story about I go shopping, buy stuff, how much discount I get, things like that. And here is on the other side is the mathematical model. So how to represent the information from the real problem into a math sentence or mathematical model that can help a student to determine the operation to use or to eventually solve the problem is really challenging to most of students, in particular to students with disabilities. So this number 3 is really the weak link that we found in when students try to translate the real world problem into a mathematical model so that they can solve the problem. So the program of my the line of my research, conceptual model-based problem solving, is really to try to address this weak link. How to help a student to translate the real world problem into the mathematical model so that it will be able to approach the problem and solve the problem. So I already mentioned about the weak link, which is really how to make the connection between the real world situation and the mathematical model. Let me introduce to you a little bit about the model when we talk about elementary mathematics. I mean, high school will be different, and other content area will be very different too. In elementary mathematics, basically we have basic 4 operations: problem solving, addition, subtraction, multiplication, and division. And to me, it's really boiled down into very simple 2 big ideas, which is the additive mathematical model that reflected the additive relationship in these problems that involve addition and subtraction. The other model relates to the underlying mathematical structure for those problems that involve multiplication and division. So you will see the model. I want to show this model to you so that it's more concrete. In additive problem solving, basically the structure is part makes up the whole. That's the bottom line. Part makes up, very simple. And of course, when you have different, when the problems has different story in terms of combining or changing the money that you have in your pocket, or comparison between 2 quantities, then each of the elements in the model will have its unique meaning when the problem situation changes. So how do I help a student to understand all these problem situation or story situation and will be able to represent the real situation into this model? That will be a very big challenge. So for that, I developed, it's called a word problem story grammar. I borrowed this concept from literature learning because most of the teachers, if you work with students in the reading comprehension, you know one of the big idea strategy is story grammar. And when we talk about a narrative story, you always have to ask your question, who's the character, what's the problem, and what's the conflict, what's the solution, and things like that. So I come up with this idea, I call it word problem story grammar. I ask the student, I want the student to ask themselves these questions so that will help them to identify the key elements in the additive problem situation, so that will help them to represent the problem into this model, basically help them identify the three elements in this model so that they will be able to represent the information into this model. Basically find out, it's actually very simple, as long as students know what is the total amount. I mean, you identify either the situation, you start with some money, you get more, eventually, okay, which amount is the total? The ending amount is the total, beginning amount is the total. Even it's in comparison situation, if I compare my amount with your amount, I mean, who has more? As long as you know who has more, or which quantity is the total amount, then you will map that information into the box that is called a whole. All the rest is the part, even the difference or the beginning.
Did you ever try it with the three boxes the same size? Is the size important? Because if the size is important, then they're just doing analogical thinking, right? They're using area to represent.
Yeah, later in our recent project, we make it the same size. So with that, don't want. Well, in the beginning, I thought the whole amount to show that the whole amount is bigger than the parts. In additive situation, it's true, but in multiplicative situation, it may not be easier to do this. But anyway, recently, actually, we modified this into the same size. And I think that's a good point.
And does it work just as well when they're all the same?
We are still doing it, so I believe it will work as well. And then this is another story situations about comparison. So then the story grammar question will be a little bit different because the situations changed. And this will be applied to multiplicative problem structure, the idea of equal groups. So these questions really can help students to map the information from the story into the model, and then the rest is very easy, very procedural. As long as you find out use algebra procedure knowledge to find out the unknown x in the equation. Well, this is one of the study that we applied this idea into solve additive and multiplicative problem solving with elementary students with learning disabilities. Ben Wise is sitting here. He is actually in this paper, made a significant contribution to the program, to this project. Let's just, I think I'm going to skip all these measures because that's going to take a lot of time. And we use not only the measure to the dependent measure involves solving problems, but also we have a measure to look at their algebraic procedure and the conceptual knowledge by developing a probe that testing on the understanding of the variable, the equation, how to solve it. So we also want to look at whether or not they gaining the algebraic knowledge and skills. We use a single subject design across the students, so that shows the students not only improve their performance from baseline to post-training assessment on researcher-developed criterion test, but also on the measure on algebra knowledge and skills, and also we use use items from standardized test PMAC to see whether or not they generalize the skills into a standardized test items. This is a multiplication before the addition subtraction, so we did it both. And another study, Dr. Zhang is also sitting here. Basically, we worked together on this project to try to apply this idea into solving more difficult problems. The problem was multi-steps, with irrelevant information and with different contexts. So hopefully they will be also able to use the model to solve more complex problems. And I think I want to skip all those because these are the measures that we used that relates to those more difficult problem structures. Students basically have to make sense from the answer, whenever they needed to round up the answer was decimals, because sometimes you talk about the bags house to the person that you really shouldn't report a decimal. And we also talk about the problem need a background information, and pictograph problems, that's more real world problems. You have to read the table, understand the information in the table. So here's the result. Again, it's a single subject design studies across, I guess, 3 students. And that shows their improvement from baseline into post-treatment measurement. And also we have a algebra measure as well to see whether or not they gain any knowledge in algebra, pre-algebra. This is another group design study, randomized assigned group into 2 conditions. So we try to see comparing this conceptual model-based problem solving with the best practice that applied in the school. So we ask the teacher from the school to teach, to deliver the instruction, not just a researcher from us. So we, of course, switched the group in the middle of the study. So both teachers from the schools and our researchers will be able to teach both situations to counterbalance the teacher effect. The best practice applied in the school is basically these solve checklist. So students were taught to search for the question and organize the information, look for the strategy, visualize, evaluate. I guess the key difference between the 2 strategies, between the conceptual model-based problem solving that I have developed and the school adopted approach, is that I explicitly teach the problem structure. So give students the structure mathematical model so they understand the part makes up a whole, or in the multiplicative situation it's either equal groups, right? But in this traditional school adopted model, they don't tell about that. Although they want a student, these are more general heuristic, although specifics are not there in terms of how to approach all those different types of problem in multiplicative problem solving. And we used repeated measure analysis, and the result, here's the result. Although I was surprised to see the result, because one of the teachers really a superstar teacher from the school district, and she, whatever student you give to her is going to produce good result, and that's in fact is the fact. However, we still found the group difference, which is very interesting and surprising. So based on a series of these studies, we actually eventually get the support from National Science Foundation to develop a software, because I want to develop a computer-assisted instructional program that will help students to learn based on their individual pace. Because we talk about these students are falling behind, and we want them to catch up, so we give them extra dosage after school if they are not surviving well in the general classroom. So I thought that would be useful for the practitioners as a supplemental curriculum, as a, let's say, tier 2 model. That's the term that we use in nowadays response to intervention environment. Can help these kids catch up with other kids. And I think the benefit is that this is a powerful tool that they can use without remember numerous rules that can help them to solve all different types of problems. So that way they will catch up with others. Since this is a powerful tool that they can use to approach all different types of problems with just 1 or 2 models, rather than many rules or many different types of problems. So we developed a software that here's the link, but we don't have time to play with it. I am going to show several screen shots of that program. Shows how we actually, Ju Young Park is here. She's mainly a screen designer. She's a very creative screen designer to help translate the idea into very fun, playful screen design for students to learn this idea. Also, Dr. Zhang's also involved in the beginning stage of the screen design. So this is teach students about the basic concept of equal groups. And not only we provide examples, but also non-example of which condition situation is not equal groups, and ask a student to make the equal groups. And this is shows the connection between the concrete model and abstract model, so they understand each element, what does all these unit rate means in a concrete way. Eventually translate into more abstract model that they can, use the procedure knowledge to solve for the unknown in the equation. And a different story situation. Here's another story situation about comparison. Comparison is a more difficult context for most of the students at the school. This is shows some of students' work after they learn that they can draw themselves. They still use the shape that we provided, although later now we do all the same shape as you suggested. And then we even go further beyond. The recent project that we worked on, a lot of team members that I presented in the beginning screen slide, that supported by a National Science Foundation, is to develop a intelligent tutor. The unique contribution of this project is to really help students also build the fundamental concept of multiplicative reasoning in this case. Because a lot of students come to our program that they don't even have the idea or the concept of composite unit, and they don't really have the basic number sense. So how we build up these by applying the constructivism approach to help them use the playful games and the concrete objects such as towers, cubes, to build up equal-sized towers for them to understand the idea of the composite unit. Because multiplicative reasoning is really about equal-sized groups. If they don't have that idea, then the rest becomes mechanical. So that's the unique contribution. Another unique contribution of this project is to see the reasoning, assess the reasoning. Because how do we see the black box? I mean, in special education, basically we look at the input-output, and we don't care about what's inside because we cannot see it or we cannot measure it. Try to understand their thinking by providing some tools that actually Ben Wise has developed, come up recently, a very good idea, user number lines, to help students show their double counting by actively involved in the manipulation of the, here's click fingers to say, hey, 1, and then you count the first group of 3, the second group of 3, so basically they can use the fingers on the screen and the number line with the idea of coordinate the two number sequences in multiplicative reasoning. So this is the bigger unique contribution of this project. The other contribution is to use cutting-edge computer science technology to really assess students on fly. So every moment is being assessed the level of student thinking, and then we will build on student level of thinking to develop or design the task for the instruction. That way, you're not just a direct instruction. Special education, typically we just say, hey, this is what I want you to learn, 1, 2, 3, 4, and you follow it. But sometimes if students don't have the background knowledge, they will not take it. If they have some knowledge, the knowledge that is conflict with your knowledge, they will kick that out. So to prevent those things from happening, we really have to build on student previous knowledge, background knowledge, and build on that and develop a task based on each individual's learning profile. So that's the unique contribution of this project. Although it's very challenging and sometimes, and the computer won't be as smart as a human being, and like people's facial expression, how do you see, right? The computer won't see if they get frustrated. And so we are dealing with these issues nowadays. It's very challenging. And how you see student reasoning. When you provide a bunch of text, multiple choices, let them pick their thinking, or the option of their thinking, or the thinking process that reflect the student thinking process. But students with disability in particular, they're not going to read the bunch of text, and probably they don't even be able to understand these choices that is provided in written. So we try to move away from these text reasoning options into several mini tools that we have been developing so that students can show their thinking process with the fingers, with the mini tools, with the number lines. That way we don't have to ask them to either verbally articulate or pick the choice that is in written. So that's the big task that we are dealing with now. These several screen basically shows how we provide heuristic prompting. This is also another aspect of the unique contribution of this project, is that we don't just tell students directly. We hopefully students will construct the concept themselves by providing the minimum heuristic and then a little bit more and more if they couldn't get it. So give them the opportunity to construct the concept themselves. These are about step-by-step provide the heuristics. And this one is make the connection between a concrete model and an abstract model. And there's various ways activities students can be involved in translate the concrete model into the abstract model, vice versa. Another way to make the connection between the concrete model problem situation and the abstract model. And also eventually we established the algebra thinking based on developed the idea of this variable. So every time you bring equal sized tower, if I ask you to bring 3 towers, next time 5 towers, 7 towers. So how do we introduce sometime one variable is changing, the changing variable we can use a letter to represent, so that this kind of connected to the algebra thinking. And that's I guess here is a summarization of the unique contribution of our current NSF project. So I think the concluding remark is that we really want to get into this black box. This thinking process before that we don't really pay attention to. We only look at the outcome, and we only look at how students solve the problem. Even students be able to solve the problem, we cannot really say, hey, they have the reasoning or they really understand the problem. You never know, because sometimes they're guessing, right? Based on the size of the number, based on whatever, or the keywords or features. And so we want to assess the reasoning part and then build on that. Hopefully we will be really address their confusion, frustrations, and give them the opportunity to construct the concept. And here's the end of my presentation, and if you have any questions. I hope I'm on time, right?
You are. We have time for a couple of questions.
So, can I call your approach or method direct instruction one, or you give the concept first?
Well, in the past, we used basically explicit direct instruction approach.
Mm-hmm.
So, although I do believe that the diagram that I developed is to tap into the conceptual understanding, tell the story about the underlying mathematical structure. But sometimes it can be easily falling into mechanics if students don't even have the fundamental concept of equal groups or multiplicative reasoning. So this recent project really tried to tap into that part to establish a fundamental idea of multiplicative reasoning or equal groups by engage students into the gameplay and use the concrete materials.
And what did the school use? So you said the school used another method or like
The school does not teach even the mathematical relations. So basically they would teach the keyword. That's a very common practice in the school. If you see times in the problem, you will multiply. But there are cases that you cannot do that. And also another strategy is a very general heuristic strategy. That's very popular. You will see all these in the school curriculum, the 4 steps. First you read the problem, you understand, you develop a plan, and then you come up with a strategy to come up with a strategy, and then you find the answer and you check your answer. But if a student does not have a strategy, how you ask them to come up with a strategy? So the explicit that relates to domain knowledge usually is not given. And that due to many factors, even the teacher does not, if the teacher does not have deep understanding of the content knowledge or domain knowledge, they will not be able to help students to develop the concept.
I'm wondering how international this is, because my children, when they were young, one started school in Germany and the other one in the US. And in Germany, they had them do all of these shape, where you would change shape and show that this group of shapes could be the same as that group of shapes. So they had this image that you could reorganize information and still have the same thing long before they talked about any numbers whatsoever. And then when they introduced the numbers were associated with those visualizations, whereas in the US it was purely, memorize these addition tables or what. Have you looked, when you did your lit review? have
Yeah,
you
this
looked
one actually is
internationally?
based on the idea come up and build a really on my international curriculum comparison.
Yeah,
Borrow some of the idea from China, because I grew up in China.
yeah.
And the idea of algebra readiness, actually they, infused the abstract thinking early on in mathematics learning, starting from even as early as second grade.
So I'm even seeing you're quite tied to numbers in the ones that you presented today. And have you thought about, when you did that
Mhm.
review, the role that other kinds of visualizations play before students even talk about numbers? And-
I guess Casey probably can speak to it, because you've read the article by, and I cannot pronounce that name. She really addressed the important role of visual representation in student problem solving process. I think speak to visual representation. I think the U.S. even does a better job than in China.
Oh, really?
Probably they really teach all these abstract stuff, rarely present a visual image of the relations. Although now they also follow U.S. the math movement, the reform also that's happening in China. So they reformed the curriculum and started to use these concrete visual representation as the building blocks. Because in the beginning you do need to have these concrete image or visual image of the relationship, rather than just give them an abstract model, because they don't understand. So I think this is really important, and also this is the unique contribution of this project, is to starting with this concrete objects, the cubes and towers, and then semi-concrete visual images, and then later connected to that. Yeah, I definitely agree. This is a very good practice. Even nowadays, China is adopting all these into their curriculum.
Yeah.
Although the pictures, not like a lot of photo pictures, irrelevant pictures in the textbook, but it is a meaningful visual representation of the situation.
It could be Germany and the Netherlands and some of those European
Probably,
countries.
I did not do
And
that, yeah.
Romania, where they have a lot of great mathematicians. I mean, it might be interesting to look at these countries
That's
where
a good
people are
idea.
mathematically gifted. and
I only did the cross-cultural comparison between China
I see.
and the U.S. because I think I can read a Chinese textbook, but German, I don't know if I can read or understand, but that would be a good, yeah.
Yeah.
Well, thank you. Let's thank you.